Hi. In this problem, we are going to look at a nice example of a problem solving strategy. So we have to evaluate this determinant. This determinant is known as the Vandermonde's determinant, and it's a famous problem, an old problem. However, we'll look at evaluating the value of this determinant in a nice and surprising way. Okay. So the determinant is pretty daunting looking. It is 1 a square till a1 power n minus 1 in the first row, and each row is similar 1 a2 square till a2 power a minus 1, and the final row is basically 1 an square and an power n minus 1. Now, of course, if we want to evaluate this determinant, we can do it in multiple ways. We can try to use some properties and simplify it a little bit. But what we'll look at here is an approach that is pretty unique. So first thing that I would like to say here is, obviously, we assume that AI is not equal to AJ for I not equal to J. So what does this mean? That if you have A's in any different rows, A1 is not equal to A2, A2 is not equal to A3, and so on. None of the A's are equal if they are in different rows. Because if they were equal, if AI was equal to AJ, then two rows will be absolutely identical, right? The ith row will be identical to the jth row, and then the determinant would be 0, right? So the determinant is 0 if any of the different AIs are equal, right? So now let's proceed to trying to evaluate the value of this determinant, right? So what we will do is we will start with a small case. Many times in problems where there are higher complexities, then it will help you if you start with a smaller case. So here what we'll start with is the case n is equal to 3, right? Let's start with the n is equal to 3 case, in which case the determinant sort of looks like this. 1a square. You can call it a1 square, but I will just label it as different variables. 1b square and 1c square. If you see, there are 3 rows because a1, a2, a3. We are taking the case n is equal to 3, right? There are 3 rows, 3 columns, and we have to find the value of this determinant. Now, obviously, you can do it by a normal method of evaluating this. But what we'll do is try to approach it through a different strategy, which will generalize well when we do the n is equal to n case. When we do the big case, we should have a strategy which generalizes, right? We don't want to evaluate it by actually calculating the determinant, right? So what I will suggest here is a process, the problem solving strategy that you can learn here is the process of generalization. So what do I mean by generalization? So instead of trying to evaluate this determinant, I will say we can replace C by a variable X. Replace C by a variable X, and then the determinant is a polynomial of degree 2. You can see that easily if you replace it by x, you will say 1a square, 1b square, and 1x square. I have replaced this determinant where c was there, I have replaced it with x, and this is clear that it will be a polynomial with degree 2. It will become a quadratic at the end, right? So what we can say is that this det is equal to some p of x, right? And the p of x is a quadratic, correct? Now, notice that if x equal to a, p of a is equal to 0. Why is that so? Because if x is equal to a, you will have the first row and the third row become exactly identical, right? 1a square, 1a square, so that the determinant is 0. So therefore, p of a is 0. Similarly, if x is equal to b, p of b is 0, right? The same logic exactly. If x is a or b, the polynomial that comes out from this becomes 0, right? So therefore, a and b are roots of the polynomial. A and b are roots of the polynomial px, right? Now, if they are roots of the polynomial, we know that by factor theorem, the polynomial can be written as capital A, some coefficient, which is the coefficient of the highest power multiplied by x minus A into x minus B, right? If it is a quadratic polynomial and we already know the two roots, obviously we can write the polynomial like this, right? Now, how do I determine the coefficient of A here? If you see here, the A is coefficient of x square in the polynomial, right? So if I want to calculate the coefficient of x square in this polynomial here in the determinant, what I should do is I should evaluate across the lower row, right? Lower row and lower column. So if I evaluate like this across this, I will get x square multiplied by this determinant, right? This determinant. So basically the cofactor of this is 1a, 1b, right? So what we will say is the coefficient of x square is basically determinant of 1a, 1b, right? And that is simple, that is simply b minus a, right? That is an easy evaluation. Coefficient of x square is coming out to be b minus a. Therefore, the polynomial becomes what? The polynomial we can write here on top. The polynomial becomes p of x is equal to, we will put the a value, which is b minus a, and multiply it with x minus a, x minus b, right? Once we have this, we know what we are going to do now. We have earlier replaced c by a variable x. Now I'll put back c. I'll say p of c. Instead of x, I'll put c now. It will become b minus a, c minus a, c minus b. That is the determinant that we were seeking. That is the value of this determinant. Do you understand what process we have followed here? What we have done is we have taken the lowest row, replaced it with a variable, then it becomes a polynomial of degree 2, and we notice that p of a and p of b is 0. So therefore we can factor the polynomial and write it like this. Once we have written it like this, the only thing that is missing is the coefficient of x square. What is that? If we evaluate across the lower row, this is the determinant, the lower determinant. Basically, this is d2, right? If this was called d3, this is d2, right? N was 3 here. If n was 2, I would have written just 1a, 1b, right? So d2 is the value of the coefficient here if I was trying to find d3, right? And then I write it as p of x is b minus a into x minus a, x minus b, and I replace x with c and I get the answer, right? Now, what will I do here in general? So if I look at the general determinant, the general determinant was like this. The general determinant looked like this: 1a2, a2 square, so on, a2 power n minus 1, and finally 1an, an square, so on, till an power n minus 1. Let's call this as dn, right? This is the determinant that we wanted to start by evaluating. I will follow the exact same method. I will say I will replace an with x. So this becomes a polynomial Pnx, right? This Pnx polynomial because the last row has become x now, right? The polynomial has degree x power n minus 1. It has degree n minus 1, right? Correct? Actually, I am wrong. I think it has degree n, because when we had a 3-degree polynomial, when it was d3, if you remember, it was 1a square, 1b b square, 1c c square. The polynomial was a quadratic. It was a quadratic. So when I have dn, okay, actually, I think I'm right. It is degree n minus 1. Sorry. So it is degree n minus 1. So polynomial has degree n minus 1 here. And we know that Pn of a1 is equal to Pn of a2 is equal to so on, Pn of a of n minus 1 is all 0. What am I saying here? I'm saying the same thing that I said for the n is equal to 3 case. I'm saying that if you replace x with a1, anytime you change x with a1, what will happen is 2 rows will become identical. So these values of the polynomial are 0, right? Therefore, Pnx can be written as capital A times x minus a1, x minus a2, and so on till x minus an minus 1, because these are the roots a1, a2, an minus 1. These are the n minus 1 roots of this polynomial, right? Great. So the only thing left for us now is to calculate the top coefficient, which we know how to do. We have to evaluate the determinant along this row and this column. So basically, we have to find out this determinant, the lower determinant here, right? Which is one step lower than the dn, right? So following the same process, you can say Pnx is equal to d of n minus 1 times x minus a1, x minus a2, and so on till x minus an minus 1, right? And now I have to replace x with an back into the original equation, and we get Pn an is equal to d of n minus 1, an minus a1, an minus a2, and so on till an minus a of n minus 1, right? And now I have reduced the question to finding a lower determinant. This is your dn, right? dn is equal to d of n minus 1 multiplied by this stuff, right? So what I have gotten now is a recursive relation. Dn is equal to d of n minus 1 multiplied by an minus a1, an minus a2, so on till an minus a of n minus 1, right? So imagine if you had a question like d4, d4 would become d3 times a4 minus a1, a4 minus a2, a4 minus a3, right? And now d3 was what? d3 we have already calculated, right? So you get a recursive relation. Now how do I generalize it and tell you the answer actually? So I'll write it like this. We have this recursive relation dn is equal to d of n minus 1. We have an minus a1, an minus a2, and an minus a of n minus 1. And what I will say now, the final result will look like this. dn will become product of k is equal to 2 to n, and inside the bracket it's another product because I want to write these. So product of I is equal to 1 to k minus 1, ak minus ai. So let me just convince you that this final answer is correct. If you are not understanding this final product, you can just work with this. This is a correct recursion. So if you need a determinant of degree 5, then you can just work downwards from there, right? But I will just convince you that this is also correct, because let's take the case D3, right? Where we are putting n is equal to 3 here, right? N is equal to 3. So this becomes, this formula gives us 3, k is equal to 2, and we have product of I is equal to 1 to k minus 1, right? And this is ak minus ai, right? Okay. So let's first assign the value of k. So first step is k is equal to 2, right? If k is equal to 2, the inside part becomes product of I goes from 1 to 1, right? 2 minus 1 is 1. I goes from 1 to 1. It is a1, a2 minus a1, right? So it is, I am putting the value of k and I am calculating this inside product. Inside product becomes a2 because a2 minus a1, right? I is 1. But there is no other factor, right? So now I have to put the value of k as 3, right? And I have to multiply because outside also there is a product. A2 minus a1 multiplied by, if I put I is equal to 1 here, I get a3 minus a1 and multiplied by, then I becomes 2. So it becomes a3 minus a2. Do you understand that this product of 3 terms is what I got earlier for D3? If you recall, D3 had come out to be, that time I had written it as A, B, C, and it had come out to be B minus A, C minus A, and C minus B, right? B minus A, C minus A, C minus B. And B you can think of as A2, A is A1, and C is A3. So see this is A2 minus A1, which is already there. This is A3 minus A1, which is here. and this is A3 minus A2, which is here, right? So for the n is equal to 3 case, it gives us the right answer, right? Let's do the n is equal to 4 case in this formula also. The n is equal to 4 case for this formula, right? So I would say this becomes, I'll just write it like this. This becomes product of k goes from 2 to 4, and here you have product of I goes from 1 to k minus 1, ak minus ai. So again, I will work by setting the k values, right? So if k is equal to 2, here you have I goes from 1 to 1, right? And you have first product is a2 minus a1, right? A2 minus a1. That's it. There is no other terms here. When k is equal to 3, we have I goes from 1 to 2, and you have second one is k is 3, a3 minus a1 multiplied by a3 minus a2 when I became 2, right? Correct. And finally, we have k is equal to 4. So I goes from 1 to 3, right? I goes from 1 to 3. So you'll have three factors here. We'll say a4 minus a1 multiplied by a4 minus a2 and a4 minus a3, right? So this is the third factor, this is the second factor, this is the first factor. You understand this is a double product. If you are not getting the logic of it, you need not use this version of the answer. You can just work with this recursion. Work with this recursion, you have to find suppose d5. You'll say d5 is equal to d4 into a4, a5 minus a1, a5 minus a2, a5 minus a3, and a5 minus a4. And then separately you can calculate d4, and you calculate d4, d4 will come in terms of d3, and then separately you calculate d3 and then put back those things. That is what actually this product formula is doing, right? But the point of the whole video is not to memorize this formula. It is not about what the final answer looks like. It is how we got to this stage, how we got this recursion. That was a very interesting process where we said that you have 1a square, 1b b square, 1c c square. And instead of calculating it directly, I replaced it by x. So it became 1x x square. It became a polynomial of degree 2. And then we noticed that PA was equal to PB was equal to 0. So the polynomial can be written as a times x minus a, x minus b. And later we calculated a. A will come out to be the lower determinant, this determinant, right? A comes out to be the lower determinant. So we got the recursion dn is equal to d of n minus 1 and similar terms, x minus a, x minus b, and other factors, right? And finally, you replace x back with c, right? So that is a very interesting process. You might not have seen that before. And hopefully you will utilize this process of generalization to solve problems for yourself. If you like the content, please subscribe to the channel, share it with your friends, and I'll see you in the next video.